Okay, so welcome back after the break. I hope that you had an amazing and delicious dinner. And now it's my honor to present our next speakers, Robert Synoczek and Szymon Madej. Robert is a FPGA design verification engineer at the Nokia Kraków Research and Development. He works on innovative projects in the field of machine learning. Machine learning used in the design and verification of 5G telecommunications systems. He also conducts research in the field of machine learning implementation on SoC FPGA devices. He completed his master's studies in automation and robotics at the Faculty of Electrical Engineering, Automatics, Computer Science and Biomedical Engineering of the AGH University of Kraków. Szymon. Szymon is a FPGA engineer at Nokia Kraków Research and Development. He works on creating innovative projects in the field of machine learning and FPGA technology in telecommunications. He also implements scenarios for verifying new FPGA functionalities for 5G telecommunications systems using the System Verilog and UVM languages. He completed his engineering studies in electrical engineering at the Faculty of Electrical Engineering of the Wrocław University of Science and Technology. Szymon and Robert, the stage is yours.
Okay, thank you. Hello, everyone. My name is Szymon, and together with Robert, I will talk a little bit about functional verification, about machine learning, and also about co-simulation. This presentation is graded as 3 out of 3 level, so advanced, but don't worry, because we are FPGA engineers, and we are used to explaining difficult things. For example, when we try to explain our jobs to our family or friends. A few words of introduction, functional verification, co-simulation, and also machine learning, a lot of topics. But in short words, we will try to present an innovative way of improving, of accelerating the process of designing digital electronics. So we will talk about functional verification, the challenges in functional verification, its place in the ASIC design flow, and also we will talk about 2 ingredients of our solution. So first, co-simulation approach, and Robert will talk about the machine learning part. Okay, so functional verification as a part of the design, ASIC design, so design of digital electronics. Let's say that we are a large company and we want to design a piece of electronics, for example, a controller for a washing machine, something like that. We need a plan, we need a specification, we need to know what we want to do. So we want a specification and description. Then we need a high-level approach to the architecture, so some kind of schematic. Then it's time for coding, done in hardware description languages like Verilog or VHDL. It looks like programming. Those are lines of code, but it really isn't. So it's quite difficult to explain, for example, to our families. And then functional verification. So the main star of this presentation, a way of ensuring that the design hidden behind lines of code will behave as intended, finding bugs or happy little accidents. Then there are a few steps that are done with the help of automatization tools like synthesis, so translating the code into a netlist of registers, logic gates, also placing and routing. So now we need to take this abstract thing, this netlist, and place it on the real resources. Then also static time analysis, because the digital design is a fine machinery of synchronized things, and everything needs to be well synchronized, like in a Swiss clock. Then another stage of verification, but with the consideration of physical phenomena, like delays, electrical current. And then manufacturing, that's last step. So back to the functional verification. Functional verification is done on the lines of code, on the abstract thing, on the design under test. We call this duty. We apply stimulus to this design under test, things like signals like clock, enable signal, input data signal, reset, and we observe results. And of course, we need to compare the results with some golden reference from some mathematical model, for example. And then we collect a measure of coverage. Is like a scoring for our testing approach. So we need to maximize the coverage of the test bench as soon as possible, as quickly as possible, using as low tests as possible to test everything. There are three main approaches to the functional verification. First is direct testing, so based on the sheer expertise, based on the knowledge. We know what we want to test. So, for example, we need to test a research stage during the runtime, for example. Then pure random approach, so literally throwing the input data into the design under test. Very naive approach, but this is necessary for me to explain the last approach that is widely used, constrained random. Basically, it is a randomness, and on top of this randomness, we have constraints based on the sheer expertise. So, for example, we can change data, input data randomly, but it doesn't make sense during the reset time. So we have a constraint on top of the randomness. That's a widely used approach. Functional verification constraint, random functional verification is a very good thing, but nowadays it's not enough. So we need to find a solution to improve this furthermore. According to the Wilson Research Group and Siemens EDA report, functional verification is very time consuming because it takes like 40 to 50% of the time spent on the whole project. Moreover, designs are getting more and more complex, so functional verification is taking more and more time. We need to find a solution because we are losing money on the functional verification. So the first ingredient of our approach is usage of co-simulation. Quite simple idea, actually, because this is a usage of some external environment, simulation environment like MATLAB, to improve the way of creating test cases or creating the reference data. In our example, we use a physical uplink shared channel IP estimation block, but that can be anything. The design under test can be anything. And we use MATLAB simulation, namely the 5G Max used in Nokia, that is based on the MATLAB language. And we also need additional wrappers between the simulation environment and the test bench with the design under test. And also we use execman tool, a very, very good tool for automating processes done in functional verification, the managing of test cases. The whole flow is done with the help of this tool. So actually that's like a first ingredient. And Robert will talk about the machine learning, which is like a real deal in this presentation. So Robert.
Thank you, Szymon. So, hi again. My name is Robert. And I'm here to present to you the recently published, actually, machine learning-based test selection for our constrained random verification environment. I mean, recently published. It was literally published and presented yesterday on the Design and Verification conference in Munich, which I came from over this night. So, by bus, yes. So let's start with a short introduction to artificial intelligence, machine learning, and deep learning. So most of you maybe have heard the word AI/ML used as a buzzword. So basically, those are three different domains, each one in the previous, which all hold one meaning, so a program that can learn and reason in a way similar to a human. So you can start with some basic algorithm for predicting the weather, or even like a game bot that tries to mimic another player. So that would be what we mean by artificial intelligence. Now, a smaller subgroup of artificial intelligence would be machine learning. These are specific algorithms that have the ability to generate and approximate models of a problem. It's basically an over-parameterized approximator for a problem. With enough data, it can easily make some basic predictions and or make some results without being explicitly programmed by a human. And then inside that, because we all hear about neural networks, there's the domain of deep learning, which utilizes deeper neural networks in the machine learning methods. So why did we decide upon calling this machine learning based? It's quite simple because we have tried many methods during the development of this project. So the premise was quite basic. We had a parameter generator for the simulation that Szymon mentioned earlier. And, well, because it's constrained random verification, you start getting a lot of very similar cases. So that's why we decided to add a test selector in between the generated test and the simulation that could decide which tests could be discarded and which ones are interesting enough to be simulated and make the functional coverage go up. So we base this on the assumption that if the tests are different enough, they should technically hit new functional coverage groups. I'm a big believer in showing also the wrong results during a machine learning project because you always hear about the successes. So to lead to a success, you have to go through quite a deep trench of wrong answers. We basically started with supervised learning. We made a data set of 2,000 tests. The sequence was randomized, labeled by a human and or by a script later. The human labeling part was just too time consuming. Took us almost a week for all those tests. And we tried some basic methods from machine learning, so support vector machines, decision trees, random forest, and even some simple neural networks. Later in time, we tried to make those 2,000 tests into a few random sequences to try out a LSTM neural network. That also didn't work. It just found a cutoff point at which it decided that every test is not interesting and you should just finish your testing. So this is the moment we thought that, yeah, maybe we need to change our approach. We tried some unsupervised learning just to, lower the amount of dimensions and see if any patterns show up. So that was the methods like factorial analysis of mixed data, t-distributed stochastic neighbor embedding, which shows you really nice graphs, and uniform manifold approximation, which is basically something close to the previous method. But that was the moment that we noticed that, yeah, that also doesn't work. We have highly overlapping clusters for the already labeled data, and we were stumped. So that looked like the end of the project. But then we noticed that maybe we're trying the wrong approach. maybe this problem isn't just a simple binary classification problem where you think that, yeah, one test is interesting, one isn't interesting. No, it actually turned out that you can redefine this as an anomaly detection problem, because you start to look for tests that are totally different. So you get an outlier that is somewhere outside the group that you usually generate. So he's basically an outlier, something you could call an anomaly. This was the moment we tried an autoencoder-based approach, which was still a simple neural network, some fully connected layers, some leaky ReLU as activations, and all the layers, almost, 5 of them, had their sizes based on the input feature space. So how many parameters we were randomizing at one time. And these input parameters had to also be normalized because the neural network would work better that way. Just the basic loss function, mean square error loss function for training. And the important part here is that we processed tests in batches. So almost like few to a few hundred tests at a time, depending on your configuration and how big your design was. So the way it worked was that you generated some simulation parameters at the beginning. So that should be to your left. Those were normalized, put into the inputs of the neural network. And now the autoencoder is called an autoencoder because it first compresses your input into a latent space, so the smallest layer in the middle there, and then tries to recreate it based on the training process. So basically, if it already trained on some inputs, it saw their distribution, learned about it, and it gets a new test, or one field in the input is totally different from what it ever saw, it cannot remake it the same as previously. So you get a bigger error at the end. You measure that error, and now you threshold based on that error. So you have a group of, we suppose, 20 tests. You sort them by the error ratio, and now you know that if the worst recreated tests should technically be the most different from what the model ever saw. So then the thresholding happened. You took those worst recreated tests, kept them for simulation, sent them onwards through the system, and discarded the rest. About that thresholding, we have tried 2 basic methods. So the most basic is you just pick some threshold of, for example, you only take the 25 worst recreated ones and keep them. That was the fixed threshold. Szymon also found a method where we could just keep the training mean square error from the previous iteration and use it as a threshold, because that's probably the error threshold at which the training data holds. So the training data consists of all the tests that it already saw, so that would be a logical conclusion. We named it MMSE, so moving mean square error. And now putting this all together, you had a test selector based on an autoencoder, a thresholding method. You would discard the tests that were recreated the best, keep the ones that were recreated the worst, and also keep them in some kind of data set for training, because with each batch of tests, you would add to that database and retrain your model. The flow gets really bad at one moment. I probably should skip this part. The only thing that we want to point out is that we kept only the 2 tools, so execman and MATLAB, and we put the autoencoder at MATLAB. It gets complicated, so don't pay too much attention to this. The results, that's the most important part. We have tried a few configurations, so we tried a few batch sizes of 25 to 100 tests. We tried all the thresholding methods, so 2 fixed ones and 1 mean square error one. We ran all those simulations a couple of times to get the mean number of tests simulated each time. And as you may have noticed, each time we get a lower amount of tests simulated than the baseline. So basically we achieved what we were trying to do. The best out of all of them, in the case of the 25 test batches, you got an almost 43% reduction in number of tests simulated with the fixed thresholding method. And in the higher batch numbers, you got a 37% reduction using the moving mean square error thresholding method. And all of this is accompanied by an only 9-second retraining and prediction time for the neural network in that whole flow. So you lose almost nothing compared to the simulation time that takes 2 to even 16 hours for a single test. So now, after publishing our results, we can confidently say that this is the first state-of-the-art neural network and co-simulation-based functional coverage closure acceleration approach that was successfully used on a commercial IP. We're not done yet. We still have to optimize the flow. So we had some problems with the regression timing where running all those tools and running all those steps took a lot of time. So we got a big overhead compared to the baseline. So not much in the case of timing, but at least we got a lower number of simulations run, which equals a lower amount of energy used for those simulations. We still need to optimize the model further. So we didn't try out too many hyperparameter configurations. We also didn't try any deeper autoencoder models. These would probably work quite fine for bigger designs. And talking about bigger designs, we will test these approaches on the bigger, higher level physical layer designs that we have. And, well, that would be everything from me. Thank you. And if there are any questions.
Thank you very much. So now it's the time for question and answers. So if you have any questions, then please raise your hands and the questions will be answered.
Okay, hi. I have a question regarding the process of generating tests. Can you please maybe repeat how tests are being generated? Because I didn't quite catch it well.
Yeah, so the process of test generation happens in 2 steps with that co-simulation approach. I'll go back to that slide. So, it was here. So it happens in 2 steps. You first have a constrained random verification environment that generates the parameters for inputs to the simulation. So that would be the first step. You have some randomized amount of, not amount, but randomized parameters in a given amount that are sent to the 5G simulation, which generates inputs and outputs for the DUT you want to test, verify. And then those inputs and outputs are sent to the regression where the test is run, basically. So the randomization and the input parameters to the model happen before the simulation step, the data generation step. And later, when we add that test selector, you add that block in between the generation, the parameter generation, and the 5G simulation.
Okay, sure, thank you.
You presented that it's simulated on one particular IP. Is this algorithm could be used in different IPs without any adjusting, or you have to trim it to work with different IPs?
It's definitely easily generalizable. So if you have the problem arises when you have a different amount of inputs for each test. So that's a problem for an autoencoder model where you have to have a given amount of inputs. That's where you need to create the test bench so that it works with this model. But generally, if you have a set amount of inputs, you can easily input this DUT into this test bench environment and reuse it. This approach could even be used for some software testing, if I'm correct, because you also may randomize some inputs to a function, and if it's big enough, you can use that model to decide which inputs are the most different, which could maybe help you in covering all the functionalities that you want.
Okay, thank you.
Generating the parameters is the key here, adjusting the parameters.
We're open to questions. No question is wrong, so we only can give the wrong answers here.
Okay, so one more question, because it seems like this problem that you're trying to solve is basically, I don't want to make a mistake here, but I think it's like set cover problem from the computation theory, because you basically want to minimize the amount of tests that are needed to cover the certain sets of certain sets of problems that you're trying to solve.
Yes.
And have you been trying maybe another approach, because it seems that the anomaly detection as a way of choosing which tests which test is basically a proper test and which is not a proper test.
Mm-hmm.
It for me it doesn't seem very. I'm not saying that this is wrong, because it's certainly working, right, as shown, but I don't quite understand how the anomaly detection is the proper way of solving the issue you're trying to solve here.
So this actually came up during the conference as well, that there are some other methods that you could use for doing this exact problem. So for example, you have the synopsis solution that helps you when you have a DUT. It can basically choose the minimal amount of tests that need to be run to cover a given amount of functional coverage points. The problem there is that they only do it based on the inputs of the DUT. And that means that you cannot configure the tests as well as you could while using another simulation that could generate those inputs. So basically you have some sequential modules in your design, and now you're testing them based on a singular input instead of sequence of inputs. And that's where this comes in, because it can filter out those tests that could be those parameter sets that could, after the simulation, generate inputs that could cover new points. There was also another approach where you could technically train a model on a given design and then ask it to generate those tests, right? Mm-hmm. So that approach would not work with constrained random verification, because your trained model does not know about those constraints. You could filter them out after, but that's basically the same thing we're doing. So, yeah. you also have to ask the question of how big your design is. Because for very small design input spaces, finding the appropriate amount of tests is quite easily computation-wise. But for really big designs, you start getting into those hours and hours of waiting to get the not optimal, let's say, but the best found approach. So yeah, it's one of the methods. There are other methods you could try, but this is just more easily generalizable to other designs, where training another model or finding that set could only be used on one design and needs to be redone on any other. And this approach is learning based on the design during the testing. Yeah.
So like, if you think the anomaly detection approach makes sense, because different tests will hit different spots in the coverage subspace. So if autoencoder sees something that it's different, then we have a greater chance that this test will hit a different spot on this coverage space.
Yeah, right. Okay, thank you.
Thank you.
Hi, thank you for very insightful presentation. Can you please tell me how you implemented the phase of retraining? Because what I understood, it took with retraining and inference a little amount of time, so just 9 seconds, I believe. So, and also a follow-up question. So, if you could compare it to the initial phase of the training of this model, how much time did it take?
So we had two phases. We basically used transfer learning with a growing data set. So the initial phase was about 300 epochs, so really short because the amount of tests was also really small at that point. With each iteration, like you can see here, we append the tests that, so let's start with the initial epoch. That's when you do not make a prediction. The model is not trained yet. You put the model through training with the whole batch that you cut out. You append those tests to the interesting test data set. Then in the next iteration, when you do a prediction, you take those tests, they go to simulation and to the interesting test data set, and the autoencoder gets not retrained, but trained with the bigger data set this time. So more of a transfer learning approach where it could be found as a little nonsensical to not retrain it from the beginning, but you rephrase to the model that those tests that it saw some time ago are still important. So it recreates those tests that it trained on even previously better than those that it saw recently. So you can still, even when covering the same points, still hit them again to just, be sure that that functionality is covered enough. Yeah. Did that cover your question, or?
Yeah, thank you. I was also asking, just for curiosity, how much time did it take to first train the model with this first epoch?
That I didn't check. The 9 seconds is a mean amount of time, and it gets longer and longer with each iteration.
Okay.
So you may get
it's quite
from
fast.
a few seconds to a few tens of seconds.
Okay.
Because those regressions were done for the lowest batches in 8 or 9 iterations. It's also helpful that we used the parallelization computation method for training in MATLAB, because that automatically divided the workload between the processors the cores that we gave it in the cloud, right? So
actually the simulation part is it takes longest.
Yeah, even if you go into minutes, you're still good because
Yeah.
at the same time the simulation is running, and those simulations take a minimum of 2 minutes for such an IP, and for the bigger ones it will take hours to days even to do one simulation. So losing minutes on the model is no problem in this time scale.
Yeah. Thank you very much.
Thank you.
Is there any other question? Okay, thank you very much for the presentation.